What if everything you know about reality is based on a lie? What if the one thing scientists have built our entire understanding of the universe on, the one constant they swore could never change, isn't constant at all? The speed of light, that sacred number, 299,792,458 meters per second, carved into the fabric of reality itself, might be the greatest assumption in scientific history. And here's what will blow your mind. There's actual evidence suggesting it might not be constant at all. Right now, as you're watching this, light is racing past you at what we call a constant speed. But what if I told you that this speed might have been different in the early universe? What if it changes depending on where you are in space-time? What if the very foundation of Einstein's relativity, the bedrock of modern physics, is built on sand? In the next 250 minutes, I'm going to take you on a journey that will fundamentally change how you see reality. We're going to explore what happens when we challenge one of science's most sacred assumptions. We're going to meet the scientists who dared to question the unquestionable. And by the end, you'll understand why this question isn't just about physics. It's about the nature of existence itself. But before we dive in, hit that like button and subscribe, because you're about to experience something that will change how you think about everything. And I want to know, where are you watching from? What country? What time is it for you right now? Drop it in the comments, because this moment, this exact configuration of space and time where you're experiencing this, is about to become a lot more interesting. Let's start with what we think we know. The speed of light in a vacuum is constant. It's always been constant. It will always be constant. That's not just a measurement. It's a law of nature, right? In 1905, a 26-year-old patent clerk named Albert Einstein published a paper that would change everything. His special theory of relativity was built on two postulates. The laws of physics are the same in all inertial reference frames, and the speed of light in a vacuum is constant for all observers, regardless of their motion. That second postulate, that's the one that broke everyone's brain. Think of it like this. Imagine you're on a train moving at 100 miles per hour, and you throw a ball forward at 50 miles per hour. To someone standing on the platform, that ball is moving at 150 miles per hour, right? Speeds add up. That's common sense. But Einstein said, light doesn't work that way. If you're on a spaceship moving at half the speed of light, and you shine a flashlight forward, that light doesn't travel at 1.5 times the speed of light. It travels at exactly the speed of light. The same speed someone standing still would measure. This wasn't just weird. It was revolutionary. It meant that time and space themselves had to be flexible to keep the speed of light constant. Time slows down when you move faster. Distances contract. Mass increases. All of this, all of IT, flows from that one assumption. The speed of light is constant. And for over a century, every experiment we've done has confirmed it. In 1887, before Einstein's paper, two scientists named Albert Michelson and Edward Morley conducted an experiment that would become legendary. They were trying to detect something called the luminiferous ether, this invisible medium that scientists thought light waves traveled through, like sound waves travel through air. Here's what they did. They split a beam of light, sent it in two perpendicular directions, bounced it back with mirrors, and recombined it. If Earth was moving through the ether, the light beam traveling in the direction of Earth's motion should take slightly longer than the perpendicular beam, like swimming upstream versus across a river. They could measure this by looking at interference patterns when the beams recombined. But here's what blew everyone's minds. There was no difference. Zero. The speed of light was the same in all directions, regardless of Earth's motion. The experiment was so precise, so carefully done, that it couldn't be dismissed, and it couldn't be explained by existing physics. This was the crisis Einstein resolved with his theory of relativity. The speed of light wasn't constant because of some property of light itself. It was constant because that's how the universe works. Space and time adjust themselves to make it so. But here's where things get interesting. What if Michelson and Morley's experiment wasn't showing us that the speed of light is constant? What if it was showing us that we can't detect changes in the speed of light using light itself? Think about it. You're trying to measure the speed of light using light. You're using rulers made of atoms, which are held together by electromagnetic forces that propagate at the speed of light. You're using clocks that tick based on atomic transitions, which also depend on the speed of light. If the speed of light changed everywhere at once, would you even notice? Your measuring devices would change too. It's like trying to measure the expansion of the universe using a ruler that's expanding at the same rate as space itself. The numbers would always look the same. This is the rabbit hole we're about to go down. And I promise you, by the time we're done, you'll never look at light the same way again. Now, before you think this is just philosophical speculation, let me introduce you to a scientist named João Magueo. In 1998, this theoretical physicist at Imperial College London published a paper that made the physics community lose their collective minds. He proposed something called VSL, variable speed of light theory. Magueo wasn't some fringe scientist. He was respected, published, credible, and he was proposing that the speed of light might have been much, much faster in the early universe, right after the Big Bang. Not just a little faster, maybe infinitely faster. Why would anyone propose something so radical? Because there's a problem in cosmology that's been bugging scientists for decades, and it's called the horizon problem. Here's the issue. When we look at the cosmic microwave background radiation, the afterglow of the Big Bang, we see that it's incredibly uniform. The temperature is the same in all directions to within 1 part in N 100,000. That's like measuring the temperature in New York and Tokyo and finding they're identical to 5 decimal places. But here's the problem. According to standard Big Bang theory, regions of space on opposite sides of the observable universe have never been in contact with each other. They've never had time to exchange information, to reach thermal equilibrium. Light hasn't had time to travel between them. So how are they the same temperature? Think of it like this. Imagine you have 2 ovens in buildings on opposite sides of Earth, and they've never been connected in any way, never shared any information. But when you measure them, they're at exactly the same temperature, down to the tiniest fraction of a degree. That would be weird, right? That would demand an explanation. The standard solution to this problem is called inflation. In the 1980s, physicist Alan Guth proposed that the universe underwent a period of exponential expansion in the first tiny fraction of a second after the Big Bang. During this inflation, space itself expanded faster than light. Regions that were once close enough to reach equilibrium were suddenly separated by vast distances. But here's what Magueo said. What if we don't need inflation? What if the speed of light was just faster in the early universe? Fast enough that distant regions could have been in contact, could have reached the same temperature? As the universe cooled and aged, the speed of light slowed down to its current value. This sounds crazy, but it actually solves several problems. It explains the horizon problem. It explains why the universe looks so flat. It even makes predictions that we could potentially test. And here's what will really blow your mind. If the speed of light was different in the past, and if Einstein's equation E equals mc is correct, then either energy or mass must have been different too. The constants we think are constant might all be variables in disguise. Magueo's work sparked a firestorm of debate. Some physicists were intrigued. Others were horrified. How dare anyone challenge Einstein's sacred constant? But the papers kept coming. Other scientists started exploring variations on the theme. The speed of light might vary with the density of the gravitational field. It might vary with the energy of the photon. It might have fluctuated randomly in the quantum foam of the early universe. And then, in 2013, something extraordinary happened. A team of physicists led by Marcel Urban at the University of Paris-Sud published experimental results suggesting that the quantum vacuum, the supposedly empty space between particles, might actually slow down light by a tiny, tiny amount. The vacuum isn't empty. It's filled with virtual particles constantly popping in and out of existence. And these virtual particles interact with light, changing its effective speed. The change is infinitesimally small, about 50 billionths of a trillionth, but it's not zero. And if it's not zero, then the speed of light isn't truly constant. It's just very, very close to constant under normal conditions. Now, before you start rewriting physics textbooks, this is still controversial. Many physicists argue that what Urban's team measured wasn't really a change in the fundamental speed of light, but rather an effective speed in a medium, like how light slows down when it passes through glass or water. But the distinction between fundamental speed and effective speed starts to blur when you realize that truly empty space might not exist. Here's where we need to pause and make sure you're still with me, because this is about to get even stranger. Let's talk about what light actually is, because if we're going to question whether its speed is constant, we need to understand what we're dealing with. For most of human history, nobody really knew what light was. Was it a particle? A wave? Some kind of emanation from the eye itself? The ancient Greeks debated it. Medieval scholars pondered it. But it wasn't until the 17th century that real progress began. In 1690, a Dutch scientist named Christian Huygens proposed that light was a wave. Waves in that mysterious luminiferous ether. Around the same time, Isaac Newton argued that light was made of particles, tiny corpuscles streaming through space. And thus began one of the greatest debates in physics history. For over 2 centuries, scientists argued. Experiments seemed to support the wave theory. Light exhibited interference and diffraction, behaviors characteristic of waves. Thomas Young's famous double-slit experiment in 1801 seemed to settle the matter. Light was definitely a wave. But then, in 1905, the same year Einstein published his special relativity paper, he published another paper explaining something called the photoelectric effect. When light hits certain metals, it knocks electrons loose. But here's the weird part. The energy of the ejected electrons doesn't depend on the brightness of the light. It depends on its frequency, its color. Bright red light won't eject electrons, but dim ultraviolet light will. Einstein explained this by proposing that light comes in discrete packets of energy called photons. Light was a particle after all. For this work, not for relativity, Einstein won the Nobel Prize. So which is it? Wave or particle? Here's the mind-bending truth. It's both. Light is both a wave and a particle simultaneously. It's what we call wave-particle duality, and it's one of the fundamental weirdnesses of quantum mechanics. When you're not looking at light, when you're not measuring it, it behaves like a wave. It can be in multiple places at once. It interferes with itself. But the moment you try to detect it, the moment you try to pin down its location, it becomes a particle, a photon, localized in space. Think of it like this. Imagine you have a friend who's simultaneously at the beach and at the mountains until you call them on the phone, at which point they suddenly have to choose one location. That's not how humans work, but that's exactly how light works. That's how all quantum particles work. Now, here's where this connects to our question about the constancy of the speed of light. If light is both a wave and a particle, which version has a constant speed? The wave? The particle? Both? In standard physics, both versions travel at the same speed, c, the speed of light. The wave nature and particle nature are just different aspects of the same underlying phenomenon. But what if they're not? What if the wave nature and particle nature of light have slightly different speeds under certain conditions? This isn't just wild speculation. In 2007, a team of physicists led by John Pendry at Imperial College London demonstrated that in certain specially designed metamaterials, materials engineered at the nanoscale, you could make the phase velocity of light, the speed at which the wave crests move, different from the group velocity, the speed at which information or energy propagates. In these materials, you can actually make light go faster than c. But before you start planning your faster-than-light starship, there's a catch. The phase velocity can exceed c, but the group velocity, the speed at which you could actually send information, still can't. Einstein's prohibition on faster-than-light signaling remains intact. But this raises a fascinating question. If we can manipulate different aspects of light speed in engineered materials, might nature do the same thing under extreme conditions? In the intense gravitational fields near black holes? In the quantum foam of the early universe? In the exotic matter that might exist in neutron stars? A scientist named John Moffat, a theoretical physicist who worked at the Perimeter Institute, has spent decades exploring these ideas. He's developed elaborate theories where the speed of light varies with the gravitational field, where it was different in the early universe, where the fundamental constants. To really understand what's at stake here, we need to talk about what happens to physics if the speed of light isn't constant. And I'm warning you now, this is where reality starts to get genuinely weird. Einstein's special relativity gives us several famous equations, but the most important one for our purposes is EMC. Energy equals mass times the speed of light squared. This equation tells us that mass and energy are interchangeable, two forms of the same thing. It's why nuclear reactions release so much energy, why the sun shines, why matter and antimatter can annihilate into pure energy. But notice what's in that equation. C, the speed of light. It's not just present, it's squared, which means it has a huge effect. If C changes, then the relationship between energy and mass changes. Let's think about what this means. If the speed of light was higher in the early universe, as Maguire proposed, then for the same amount of mass, you'd have more energy. E equals mc. If C is bigger, E is bigger. The early universe would have been more energetic than we currently calculate, even with the same amount of matter. But it gets weirder. The speed of light appears in almost every fundamental equation in physics. Maxwell's equations describing electromagnetism, the Schrödinger equation in quantum mechanics, Einstein's field equations describing gravity. If C isn't constant, all of these equations need to be modified. A physicist named Andreas Albrecht, working at UC Davis, explored some of these implications in the late 1990s. He showed that if the speed of light varied, in the early universe, it would leave specific signatures in the cosmic microwave background, particular patterns of temperature fluctuations, specific statistical properties that we could look for. And here's where it gets exciting. When we started getting really precise measurements of the cosmic microwave background from satellites like WMAP and Planck, we started finding anomalies, things that don't quite fit the standard model of cosmology. A mysterious axis of evil, where the universe looks less random than it should, cold spots that shouldn't exist, asymmetries that demand explanation. Could these anomalies be evidence of a varying speed of light? Most cosmologists say no. They're more likely just statistical flukes or effects we don't fully understand yet. But a minority of researchers look at these anomalies and see hints of something deeper. Now let's think about what a varying speed of light means for time itself. In relativity, space and time are linked. They're not separate entities, but aspects of a four-dimensional space-time. The speed of light is the conversion factor between space and time. It tells you how much space equals how much time. Think of it like an exchange rate between currencies. If I tell you that $1 equals 0.85 euros, I'm giving you a conversion factor. The speed of light is the conversion factor between space and time. 1 second equals 299,792,458 meters. That's not arbitrary. It's fundamental to how space-time is structured. So if the speed of light changes, the relationship between space and time changes. A second of time would correspond to a different amount of space. Time itself would flow differently. Here's a thought experiment that will make your brain hurt. Imagine the speed of light suddenly doubled everywhere in the universe right now. What would you experience? At first, you might think everything would suddenly move in slow motion, or you'd be able to see things happening at twice the speed. But here's the twist. You wouldn't notice anything at all. Why? Because all your perception, all your thoughts, all the chemical reactions in your brain, all the light entering your eyes, everything depends on the speed of light. If it doubled everywhere at once, including inside your atoms, inside your brain, you'd have no way to detect the change. It's like asking what you'd experience if all of space suddenly doubled in size. Nothing, because your measuring sticks would double too. This is the deep problem with testing whether the speed of light is constant. We're trapped inside the system. We're trying to measure the measuring stick using the measuring stick itself. But here's where quantum mechanics offers us a potential way out. In quantum theory, different aspects of reality can be in superposition, existing in multiple states simultaneously until measured. What if the speed of light itself is in a quantum superposition? What if it's many different values at once and only collapses to a specific value when we measure it? A team of researchers led by Václav Bruckner at the University of Vienna has been exploring these ideas. They've shown that in quantum theory, the causal structure of spacetime itself can be indefinite. Events can be in a superposition of happening before and after each other. If that's possible, might the speed of light also be fundamentally uncertain until measured? These ideas are still highly speculative, at the very edge of what we understand about quantum mechanics and relativity. But they're being taken seriously by reputable scientists at major research institutions. We're not talking about pseudoscience here. We're talking about the frontier of physics. Before we go deeper, let me ask you something. How are you feeling right now? Is your conception of reality starting to crack a little? Good. That means you're really understanding what's at stake. Because we're about to go even further down the rabbit hole, let's talk about time. Because if the speed of light isn't constant, then time itself might not be what you think it is. In everyday experience, time seems absolute. It flows at the same rate for everyone. A second is a second is a second, whether you're sitting still or moving, whether you're on Earth or on Mars, whether you're young or old. But Einstein showed us this is an illusion. In special relativity, time dilation occurs when you move at high speeds. The faster you go, the slower your clock ticks relative to someone who's standing still. This isn't some abstract mathematical quirk. It's real and measurable. GPS satellites have to account for time dilation, or they give you wrong directions. Particle accelerators see subatomic particles that should decay in microseconds, lasting much longer because they're moving at near light speeds. But all of this, all of time dilation, follows from the assumption that the speed of light is constant. The math works like this. If light has to travel the same speed for all observers, and you're moving at high speed, then time must slow down for you to make the numbers work out. Think of it like this. Imagine you're on a train watching a beam of light bounce between two mirrors, up and down, tick-tock, like a clock. To you, the light is just bouncing straight up and down. But to someone standing on the platform watching the train go by, that light is also moving forward with the train, so it's tracing out a diagonal path. The light has to travel a longer distance from their perspective. But the speed of light is the same for everyone. So if the light is traveling a longer distance, but at the same speed, it must take more time. But it's the same events. The only way to resolve this is that time itself is running slower on the train. Your clock is ticking slower than the platform observer's clock. This is time dilation, and it's been confirmed in thousands of experiments. But here's the key insight. It only works if the speed of light is constant. If the speed of light could vary, you wouldn't need time dilation. You could keep absolute time and just let the speed of light be different for different observers. In fact, there are theories called Lorentz ether theories, developed in the late 19th and early 20th centuries, that explain all the same phenomena as special relativity, but using a different framework. In these theories, there's a preferred reference frame, an absolute space, and time is absolute. Objects physically contract when they move through this space, and the speed of light really does depend on your motion through the ether. The kicker? Lorentz ether theories make exactly the same predictions as special relativity for all experiments we can currently do. They're empirically equivalent. The only reason we prefer Einstein's relativity is philosophical. It's more elegant, more symmetric, doesn't require a preferred reference frame. But mathematically, both frameworks work. This raises a profound question. Are we choosing our physics based on elegance rather than truth? Is it possible that Lorentz was right, that there is an absolute space and time, but the speed of light varies in just the right way to make it look like relativity is correct? Now, before you think I'm advocating for throwing out Einstein, I'm not. Special relativity has been one of the most successful theories in all of science. But I want you to understand that our belief in the constancy of the speed of light is partly empirical and partly philosophical. We've chosen to interpret our observations in a particular way. Here's where it gets even stranger. In general relativity, Einstein's theory of gravity, the speed of light isn't actually constant in a global sense. It's only locally constant. Let me explain what that means. In general relativity, gravity isn't a force, it's the curvature of spacetime. Massive objects like stars and planets bend spacetime around them, like a bowling ball on a trampoline. And in curved spacetime, the speed of light measured by a distant observer can appear to change. For example, light passing near the sun slows down slightly from the perspective of an observer far from the sun. Not because the photons are moving slower through space, but because spacetime itself is stretched near the sun. The light has to traverse more distance. Think of it like this. Imagine ants walking on a rubber sheet at constant speed. If you stretch part of the rubber sheet, the ants crossing that region would appear to slow down from your perspective, even though from their perspective, they're walking at the same speed. That's what happens to light in curved spacetime. This means that in a very real sense, the speed of light does vary in general relativity. It varies with the gravitational field. An observer hovering just above the event horizon of a black hole would see light from the outside universe arriving at incredibly high speeds, while an observer far away would see light near the black hole slowing to a crawl as it approaches the horizon. From this perspective, asking whether the speed of light is constant is like asking whether straight lines exist in a curved space. It depends on how you measure, depends on your perspective, depends on the structure of spacetime itself. A physicist named Jacob Bekenstein, who tragically passed away in 2015, spent much of his career exploring the idea that the fundamental constants of nature might not be constant. He developed theories with a fine structure constant, which governs the strength of electromagnetic interactions, varies over cosmological time. And if the fine structure constant varies, it suggests that other constants, potentially including the speed of light, might vary too. Bekenstein's work led to some fascinating predictions. If these constants changed over the lifetime of the universe, we should see different physics in distant galaxies, which we observe as they were billions of years ago. Some controversial observations have suggested exactly this. Anomalies in the spectra of distant quasars that could indicate different physical constants. Most of these observations have been disputed, explained away as measurement errors or instrumental effects. But not all of them. There remain tantalizing hints that something weird is going on. Are you still with me? Because we're about to connect all of this to something even more profound. Let me tell you about one of the strangest ideas in modern physics, the holographic principle. And this connects to the speed of light in ways that will absolutely blow your mind. In the 1990s, physicist Leonard Susskind, building on work by Gerard 't Hooft, proposed something radical. They suggested that all the information in a three-dimensional region of space can be encoded on its two-dimensional boundary. The universe, in this view, is like a hologram. The three-dimensional reality we experience is a projection from information stored on a distant two-dimensional surface. This sounds like science fiction, but it comes from taking the physics of black holes seriously. When Stephen Hawking showed that black holes have entropy, a measure of disorder or information, he found something strange. The entropy of a black hole is proportional to the area of its event horizon, not its volume. Think about that. If you have a box filled with gas, the amount of information needed to describe that gas, the positions and velocities of all the molecules, depends on the volume of the box. More volume, more molecules, more information. But for a black hole, the information depends on the surface area. It's like discovering that everything you know about a library is written on its walls, not in the books on its shelves. The interior is redundant, emergent, derived from the boundary. Susskind and 't Hooft proposed that this isn't just true for black holes. It's true for the universe as a whole. We're all holograms, three-dimensional projections from information encoded on a distant two-dimensional surface. Now, here's where this connects to the speed of light. In a holographic universe, the speed of light isn't a fundamental property of reality. It's an emergent property arising from the underlying information-theoretic structure of the holographic encoding. Think of it like pixels on a screen. When you watch a video, things move across the screen at various speeds. But those speeds aren't fundamental properties of the screen or the pixels. They're properties of the information being displayed. The speed of a moving object in the video emerges from how rapidly the pixel values are changing. If the universe is holographic, the speed of light might be similar. It's not that photons are physical objects moving through space at a certain speed. It's that information propagates through the holographic encoding at a certain rate, and we perceive this as light moving at speed c. And here's the kicker. If the holographic encoding changes, if the fundamental information-theoretic structure of reality shifts, then the effective speed of light could change too. It would be like changing the frame rate of a video. The apparent speed of objects in the video would change, even though nothing real about the video itself has changed. Juan Maldacena, a physicist at the Institute for Advanced Study, made this connection explicit with his famous AD-SCFT correspondence in 1997. He showed that a theory of quantum gravity in a higher dimensional space is mathematically equivalent to a quantum field theory without gravity on the boundary of that space. It's the most concrete realization of the holographic principle we have. In AD-SCFT, the speed of light in the bulk, the interior space, is related to properties of the boundary theory, and those properties can change. The boundary theory can have different parameters, different coupling constants, which would manifest as different speeds of light in the bulk. This is still theoretical, still speculative. We don't know if our universe is actually holographic. We don't know if AD-CFT applies to our spacetime. But it shows that there are rigorous mathematical frameworks in which the speed of light genuinely isn't fundamental. Let's think about what this means experientially. If you're a hologram, a pattern of information projected from a distant boundary, what does motion even mean? When you walk across a room, are you moving through space? Or is the holographic projection simply updating, changing the encoded information in a way that we interpret as movement? Here's an analogy. Think of a character in a video game. Mario doesn't actually move through the game world. The pixels on the screen change in a coordinated way that creates the illusion of movement. Mario is a pattern of information being updated in the computer's memory and displayed on the screen. If the holographic principle is correct, you're Mario. You're a pattern of information being updated on a cosmic computer. Your movement through space, the propagation of light, the flow of time. All of these are aspects of how the information is being processed and displayed. And if that's true, then asking whether the speed of light is constant is like asking whether the frame rate of the universe is constant. It might be. It might not be. It depends on the fundamental information processing substrate of reality, which we don't understand yet. This is getting pretty heavy, so let me ground it with something concrete. Researchers are actually trying to test whether we live in a hologram. One experiment, conducted at Fermilab near Chicago, uses incredibly sensitive interferometers to look for quantum jitter in spacetime, fluctuations that would arise if space is pixelated at the Planck scale, the smallest possible scale allowed by quantum mechanics. If space is pixelated, if it's fundamentally discrete, like the pixels on a screen rather than continuous, that would be strong evidence for the holographic principle. And it would mean that concepts like the speed of light are emergent, arising from deeper discrete structure. So far, these experiments haven't found anything definitive, but they're still running, getting more sensitive, probing deeper into the structure of reality. Can you feel it? Can you feel your certainty about reality starting to dissolve? We're not even halfway through yet. Stay with me. Now I want to talk about something that will change how you think about cause and effect, retrocausality. The idea that the future can influence the past. And yes, this connects to the speed of light. In standard physics, causality flows forward in time. Events in the past cause events in the present, which cause events in the future. This seems obvious, but quantum mechanics throws a wrench into this intuitive picture. In 1978, physicist John Wheeler proposed a thought experiment called the delayed choice experiment. Here's how it works. You send a photon toward a beam splitter, a device that gives the photon a 50% chance of going one way and a 50% chance of going another way. You can set up the experiment two different ways. In the first configuration, you put detectors on both paths. The photon will act like a particle and definitively take one path or the other. In the second configuration, you recombine the two paths with mirrors and another beam splitter, and you look for interference. In this case, the photon acts like a wave, taking both paths simultaneously. Here's the twist. Wheeler proposed waiting until after the photon has passed the first beam splitter to decide which configuration to use. You make your choice about whether to look for particle behavior or wave behavior after the photon has supposedly already decided whether to be a particle or wave. And here's what experiments have shown. It works. Your choice in the present affects how the photon behaved in the past. When you choose to look for wave behavior, the photon retroactively takes both paths. When you choose to look for particle behavior, the photon retroactively takes one path. This has been confirmed in real experiments, not just thought experiments. In 2007, a team led by Alain Aspect in France performed a delayed choice experiment over distances of 48 meters. The choice of measurement was made after the photon had already passed the decision point, and the results matched Wheeler's prediction perfectly. What does this have to do with the speed of light? Everything. Because if the future can influence the past, then the notion of information propagating forward in time at the speed of light breaks down. Information, or at least influence, can propagate backward in time too. Some physicists have taken this further. John Cramer developed something called the transactional interpretation of quantum mechanics in the 1980s. In his framework, quantum events involve waves propagating both forward and backward in time. A measurement in the future sends an echo backward in time that influences the past, creating the present reality through a transaction between future and past. In the transactional interpretation, the speed of light isn't just about forward propagation. There's also backward propagation. Photons are described by waves moving forward in time from the source and backward in time from the detector. And the quantum state that actually occurs is where these waves meet and create a standing wave. Think of it like this. Imagine you're shaking one end of a rope, creating waves that propagate toward the other end. Someone at the far end shakes their end too, creating waves coming back toward you. Where the two wave patterns meet, you get a standing wave, a stationary pattern of oscillation. That standing wave is the realized physical state. In this view, causality is a two-way street. The past influences the future, yes, but the future also influences the past. And the speed at which influence propagates, both forward and backward, might not be the same. It might depend on the quantum state, on the measurement being made, on the structure of spacetime between the events. Now, this interpretation is controversial. Most physicists prefer the Copenhagen interpretation or the many worlds interpretation. But the transactional interpretation makes the same predictions as other interpretations for all experiments we can currently do. It's another case where we're choosing our interpretation partly on philosophical grounds. Here's where it gets really wild. If retrocausality is real, if the future can influence the past, then experiments we do in the future could affect measurements of the speed of light in the past. The act of measuring whether the speed of light has changed could itself cause or prevent the change. This sounds paradoxical. How can measuring something change, whether it was always constant? But in quantum mechanics, this kind of thing happens all the time. Measurement creates reality. Before you measure, quantum systems are in superposition, existing in all possible states at once. The act of measurement collapses the superposition, forcing reality to choose. What if the constancy of the speed of light is a quantum superposition that gets collapsed by our measurements? What if, in some sense, light is traveling at all possible speeds simultaneously, and our experiments force it to choose one speed, retroactively creating a history where that was always the speed? A physicist named Yakira Haranov has explored these ideas extensively. He developed something called the two-state vector formalism, which describes quantum systems using both a forward-evolving state from the past and a backward-evolving state from the future. In his framework, the present is determined by boundary conditions from both directions in time. Aharanov's work has led to some genuinely bizarre predictions that have been experiment-ally confirmed. Things like weak measurements, where you can extract information about a quantum system without collapsing it completely. Or the quantum Cheshire cat effect, where you can separate a particle from its properties, like separating the grin from the Cheshire cat. If these weird quantum effects are real, and they seem to be, then our entire notion of causality needs revision. And if causality isn't what we thought, then the speed of light, which defines the causal structure of spacetime, might not be what we thought either. Here's a practical example that will make this concrete. Imagine you're doing an experiment to measure the speed of light. You send a photon from point A to point B and measure how long it takes. Simple, right? But in quantum mechanics, until you measure the photon at point B, it's in a superposition of having taken all possible paths, including paths that involve going faster than c, slower than c, or even backward in time. When you detect the photon, the wave function collapses, and reality retroactively decides which path the photon took. The average over all these paths gives you the classical speed c. But individual quantum trajectories can be faster or slower. Some physicists have even calculated that quantum uncertainty allows for temporary violations of the speed of light limit over very short distances and time scales. Photons can tunnel through barriers faster than c. They can take shortcuts through quantum fluctuations in spacetime. Over macroscopic distances, these effects average out, and you get the classical speed of light. But at the quantum level, the speed of light is more like a speed limit you can temporarily exceed as long as you don't get caught, like doing 80 in a 65 zone for a few seconds. Now let me connect this to something else that will blow your mind: quantum entanglement. When two particles are entangled, measuring one instantly affects the other, no matter how far apart they are. Einstein called this spooky action at a distance and hated it. It seemed to violate his prohibition on faster-than-light information transfer. But here's the subtle point. Entanglement doesn't let you send information faster than light. When you measure one particle, its entangled partner is instantly affected, but you can't control what result you get. The correlations between the particles only become apparent when you bring the measurement results together and compare them, which requires classical communication at the speed of light or slower. However, some physicists have proposed that the instant correlation in entanglement suggests there's a deeper level of reality where space and time don't work the way we think. A level where the speed of light isn't relevant because distance itself isn't fundamental. Anton Zeilinger, an Austrian physicist who won the Nobel Prize in 2022 for his work on quantum entanglement, has done experiments demonstrating entanglement over distances of more than 1,200 kilometers using satellites. The correlations persist regardless of distance, suggesting that at some level, the entangled particles aren't really separate. Space itself is emergent, not fundamental. If space is emergent, if distance is an illusion arising from deeper quantum information, then the speed of light is just describing how this illusion of space unfolds. Change the underlying quantum information structure, and you change the apparent speed of light. Are you starting to see the pattern? Every direction we look in modern physics, we find hints that the constancy of the speed of light might be an approximation, valid in our everyday world, but breaking down at the extremes. The very early universe, near black holes, at quantum scales, in the presence of exotic matter or energy. But we're not done yet, not even close, because now we need to talk about what this means for you personally. Let's take a breath and bring this back to Earth, to you, to your life, because here's what will really blow your mind. If the speed of light isn't constant, if it's been changing over the history of the universe, then you are not who you think you are. Your body is made of atoms. Those atoms are held together by electromagnetic forces. Electrons orbit atomic nuclei, and the strength of that attraction depends on the fine structure constant, which is intimately related to the speed of light. If the speed of light was different when those atoms formed, they would have different properties. The chemistry of life depends on precise relationships between atomic energy levels. The way DNA molecules form, the way proteins fold, the way neurons fire in your brain, all of this depends on electromagnetic interactions that depend on the speed of light. If the speed of light has been changing slowly over cosmic time, then the atoms in your body, the molecules that make you you, are different from how they would have been a billion years ago. Not dramatically different, but subtly different. And those subtle differences would accumulate over time. Think about it like this. Imagine you're a sculpture, but instead of being carved from marble, you're carved from space-time itself, from the fields and particles that fill the universe. If the properties of space-time change, if the fundamental constants shift, then you change too. You're not a fixed object. You're a dynamic pattern maintaining itself in a changing substrate. But here's what's even wilder. Your consciousness, your thoughts, your perception of time, all of this is implemented in neural processes that depend on the speed of light. When neurons fire, electrical signals propagate through your brain. When you see something, photons enter your eyes and trigger chemical reactions in your retina. When you think, quantum processes in microtubules might be involved, according to some theories. If the speed of light were different, would you think differently? Would you perceive time differently? Would you even be conscious in the same way? There's a principle in physics called cosmological natural selection, proposed by Lee Smolin in the 1990s. He suggested that universes with different physical constants might give birth to baby universes through black holes, and universes with constants conducive to forming lots of black holes would have more offspring. Over time, the multiverse would evolve toward constants that maximize black hole production. In Smolin's scenario, the constants we observe, including the speed of light, aren't arbitrary. They're selected by a kind of cosmic evolution. We live in a universe with this particular speed of light because universes with this speed of light are good at reproducing. Let's go deeper into time itself. Because if the speed of light can vary, then time as we understand it might be an illusion. In physics, time is what clocks measure. But what is a clock? At the most fundamental level, a clock is any periodic process. The oscillation of a pendulum, the vibration of a quartz crystal, the transition between energy levels in an atom. These processes define what we mean by time. The most precise clocks we have are atomic clocks, which use the oscillations of cesium or strontium atoms. These clocks are so precise that they won't lose a second in hundreds of millions of years. And in fact, the SI definition of the second is based on atomic clocks. 1 second is defined as exactly 9,192,631,770 periods of the radiation, corresponding to a specific transition in cesium-133. But here's the thing. Atomic transitions depend on electromagnetic interactions. They depend on the speed of light. If the speed of light changed, the frequency of these transitions would change. Your atomic clock would tick at a different rate. So when we say, the speed of light has been constant over time, what we really mean is, the speed of light measured using atomic clocks that depend on the speed of light has been constant. We're using light to measure light. It's circular. Think of it like this. Imagine you're trying to determine if a rubber band is stretching by measuring it with another rubber band. If both rubber bands stretch at the same rate, you'll always measure the same length, even though both are changing. This is called the problem of time in physics, and it's been bothering physicists for decades. How do you measure change without assuming something is constant to measure against? How do you define time without begging the question? One solution is to look for processes that don't depend on the speed of light. Gravitational processes, for instance. The orbital period of a binary pulsar depends on gravity, not electromagnetism. If you could use gravitational clocks to measure time and compare them with atomic clocks, you could potentially detect changes in the speed of light. This has actually been done, in a sense. Astronomers observe binary pulsars, pairs of neutron stars orbiting each other. These systems lose energy to gravitational waves, causing their orbits to decay at a predictable rate. The timing of pulsar pulses gives us a gravitational clock. Comparing pulsar timing with atomic clocks over decades has shown no evidence that the speed of light is changing, at least not by any amount we can currently detect. But the precision is limited. A change of 1 part in a billion per year would be undetectable. Now here's where it gets really weird. Some physicists have proposed that time itself might not be fundamental, that what we call time is actually an emergent phenomenon arising from something deeper. Julian Barber, a British physicist, has spent his career developing a theory he calls timeless physics. In his view, the universe doesn't evolve through time. Instead, the universe is a vast space of possible configurations, and what we perceive as time is simply a path through this space of configurations. Think of it like a movie. A movie is a sequence of still frames. Each frame exists simultaneously on the film strip. There's no inherent flow from one frame to the next. But when you watch the movie, you perceive motion, change, time. The time you experience is emergent, arising from the relationship between the frames, not from any actual flow. In Barber's timeless universe, each moment exists eternally. The universe doesn't change, it simply is, all moments laid out in a vast timeless space. What we perceive as change is our consciousness navigating through this space, experiencing one moment after another. And in such a universe, the speed of light is not about motion at all. It's about the geometric relationships between different moments, different configurations. A high speed of light means nearby moments are far apart in configuration space. A low speed of light means they're close together. Changing the speed of light would be like changing the metric, the distance function, on the space of configurations. It would change which moments count as nearby and which count as distant. This sounds abstract, but it has concrete mathematical formulations. Barber has worked out the quantum mechanics of timeless systems, and it makes the same predictions as standard quantum mechanics for all experiments we can do. It's empirically equivalent, just conceptually different. And here's why this matters for our question. In a timeless universe, asking whether the speed of light changes over time is a category error. Time doesn't exist fundamentally, so nothing can change over time. What we perceive as changes in the speed of light would actually be variations in the geometric structure of the configuration space. Another physicist exploring similar ideas is Carlo Rovelli, one of the founders of loop quantum gravity. In his view, time is relational. It doesn't exist independently, but only emerges from the relationships between physical systems. When you say the speed of light is constant over time, you're really saying the ratio between the speed of light and some other physical process is constant. But that ratio depends on which process you choose as your reference clock. Different choices might give different answers. In Rovelli's framework, there's no absolute time, no universal clock. There are only local times, defined by local physical processes. And these local times can run at different rates depending on the gravitational field, the motion, the quantum state. The speed of light in this view is not a speed in the sense of distance per time, because there's no universal time. It's better thought of as a ratio between spatial and temporal aspects of space-time events, and that ratio can be different for different observers, different reference systems. Let me make this personal again. Your experience of time, the sensation of moments flowing one after another, is implemented in neural processes in your brain. Neurons fire, chemicals diffuse, electrical signals propagate. All of these processes define your subjective time. But these processes depend on the speed of light. The electromagnetic interactions that hold molecules together, that allow neurons to fire, that implement your consciousness, all propagate at speed c. Your subjective time is calibrated to this speed. If the speed of light changed, your subjective time would change too. You wouldn't experience it as time speeding up or slowing down. You'd experience it as, what? A shift in the quality of experience? A feeling that reality has become more or less dense. We don't have words for it because we've never experienced it. But here's something you can test right now, in your own experience. Close your eyes for a moment. Notice your thoughts. Notice how they seem to flow, one arising, persisting for a moment, then fading as the next arises. That flow, that sense of mental time, is your consciousness navigating through its state space. Now ask yourself, is that flow real? Or is it an illusion created by the structure of your memories? Each moment of your consciousness includes memories of previous moments. You remember the previous thought, and that memory creates the illusion that the previous thought was before the current thought. But maybe all moments of your consciousness exist simultaneously, timelessly, and the sense of flow is just a pattern in how these moments are related, how they contain information about each other. If that's true, then the speed of light is not about time at all. It's about the structure of information in the timeless space of all possible experiences. And changing the speed of light would change that structure, would change which experiences count as connected and which count as separate. This is getting very deep, very philosophical, but it's grounded in serious physics. The problem of time, the relationship between consciousness and physical law, the emergent nature of causality, these are all active research areas. And they all suggest that the question, is the speed of light constant, is not as simple as it seems. It depends on what you mean by constant, what you mean by speed, and most fundamentally, what you mean by time. Now let's bring this full circle. Let's talk about what all of this means for the biggest questions. Where did the universe come from? What is reality? Why do we exist? If the speed of light isn't constant, if it can vary with time, space, energy, gravitational field, or quantum state, then the universe as we understand it is radically different from what we thought. The Big Bang, the idea that the universe began in a hot, dense state 13.8 billion years ago and has been expanding ever since, is built on assumptions about the constancy of physical laws, including the speed of light. If those laws were different in the early universe, then our entire picture of cosmic history needs to be revised. João Magueio and others have shown that if the speed of light was much higher in the early universe, you don't need the inflationary scenario. You don't need a period of exponential expansion faster than light. The universe could have expanded at a more sedate pace, and the high speed of light would have allowed distant regions to reach equilibrium anyway. This is important because inflation, despite its successes, has some serious problems. It requires a special kind of field, the inflattened field, that we've never detected. It makes predictions about the spectrum of gravitational waves that we haven't confirmed yet. And it leads to eternal inflation, where bubble universes keep forming forever, creating an infinite multiverse that's arguably untestable. If VSL theory is correct, you might not need inflation at all. The universe could be simpler, more elegant, or at least differently complicated. But there's a deeper implication. If fundamental constants can vary, if the laws of physics are not eternal and unchanging, then the universe is more like a living organism than a machine. It evolves. It adapts. Its laws change as it matures. This connects to ideas from Lee Smolin and others about cosmological natural selection. If universes can reproduce through black holes, and if the fundamental constants can vary between parent and child universes, then the constants we observe are the result of a selection process. They've been optimized, in a sense, for producing black holes, which means optimized for producing stars, which means optimized for complexity. And if the universe is optimized for complexity, then our existence, the existence of conscious observers capable of asking these questions, is not an accident. It's a feature, not a bug. Now, I want to be careful here. This doesn't mean the universe was designed for us. It doesn't mean there's a purpose or a plan. It means that in a multiverse of varying constants, we inevitably find ourselves in a universe where the constants allow for our existence. And those constants might have been shaped by a selection process that favors complexity. But here's where it gets truly profound. If consciousness is implemented in physical processes that depend on the speed of light, and if the speed of light has been shaped by cosmic evolution to favor complexity, then consciousness itself might be a cosmic phenomenon, not just a terrestrial accident. Think about it. We're made of atoms forged in stars. Carl Sagan famously said we're made of star stuff. But it goes deeper than that. We're made of quantum fields governed by constants that have been shaped by cosmic evolution. We're not just in the universe, we're of the universe. We're the universe becoming aware of itself. And if the speed of light is not a fixed constant, but a parameter that can vary, that has varied, it might vary again in the future, then we're part of a cosmic story that's still being written. The universe hasn't finished evolving. The laws of physics haven't reached their final form. This brings us to the ultimate question. Could we, in principle, change the speed of light? Could a sufficiently advanced civilization manipulate the fundamental constants? It sounds like science fiction, but some physicists have seriously explored this. If the constants are really fields permeating space, like the inflattened field in inflation, or the Higgs field that gives particles mass, then manipulating those fields would change the constants. You'd need incredible energies, probably comparable to those in the early universe. But in principle, it's not impossible. A civilization that could manipulate space-time curvature, create artificial black holes, tap into vacuum energy, might be able to alter local physics. And here's a wild thought. If such manipulation is possible, it might already be happening. Some of the anomalies we observe in cosmology, The things that don't quite fit our models might be the signatures of universe engineering by advanced civilizations. The physicist James Annis has speculated about this. He's asked, if civilizations could manipulate cosmic constants, what would the universe look like? It might look like a patchwork of different domains, each with slightly different physics, tuned for different purposes. Maybe some domains are optimized for computing, with constants that allow for dense information processing. Maybe some are optimized for energy production, with constants that make fusion or matter-antimatter annihilation more efficient. Maybe some are optimized for consciousness, with constants that allow for richer forms of experience. We might be living in one such domain, and the speed of light we observe might not be the natural value at all. It might be an engineered value, optimized for the kind of complex chemistry and biology that leads to beings like us. I'm not saying this is true. I'm saying it's consistent with what we know, and it illustrates just how radical the implications are if the speed of light isn't truly constant. Here's the most mind-bending possibility of all. If we could change the speed of light, we could change the past. Remember retrocausality? Remember how quantum measurements in the present can affect the past? If the speed of light governs the causal structure of spacetime, then changing it would change what counts as cause and effect. You could potentially create closed time-like curves, loops in spacetime, where an event is its own cause. You could send information backward in time. You could alter history. The physicist Kip Thorne, who won the Nobel Prize for his work on gravitational waves, has explored the physics of time travel using general relativity. He's shown that wormholes, if they could be stabilized with exotic matter, could in principle connect different times as well as different places. But wormholes require exotic matter with negative energy density. We don't know if such matter exists. However, if the speed of light can vary, and if E equals mc, then there might be states where the effective energy is negative. Regions where the speed of light is imaginary, where time and space swap roles. This is highly speculative, at the very edge of theoretical physics. But it's based on real equations, real solutions to Einstein's field equations. The universe is stranger than we imagined. And that brings me to what I want you to feel right now. Wonder. Not just intellectual curiosity, but genuine awe at the vastness of what we don't know. The speed of light, this number that seems so fixed, so certain, might be a doorway to a completely different understanding of reality. Every scientific revolution begins with someone questioning an assumption everyone else took for granted. Copernicus questioned whether Earth was the center of the universe. Darwin questioned whether species were fixed and unchanging. Einstein questioned whether space and time were absolute. And now, physicists are questioning whether the speed of light is truly constant. What if the next revolution is already beginning? What if the papers being published right now, by Maguire, by Moffat, by the researchers looking for quantum gravity effects, what if they're the first hints of a transformation in understanding as profound as anything that's come before? You're living through this moment, right now. As you watch this, there are experiments running, telescopes observing, theorists calculating, all trying to answer this question. And within your lifetime, we might know the answer. That should fill you with excitement. Because if the speed of light isn't constant, if it can be different, if it has been different, then the universe is not a static stage on which the drama of existence plays out. It's a dynamic, evolving, living entity, and we're part of that evolution. Let me tell you about something that's going to change how you think about your place in all of this. The anthropic principle. Not just as an abstract idea, but as a lived reality that connects you personally to the cosmic question of varying constants. The anthropic principle comes in two forms. The weak anthropic principle says that we observe the universe to have properties compatible with our existence, because if it didn't have those properties, we wouldn't be here to observe it. It's a selection effect, like observing that you always find fish in water, not because fish magically create water, but because you only find living fish where there's water. A strong anthropic principle goes further. It suggests that the universe must have properties compatible with the eventual emergence of conscious observers. This is more controversial because it seems to imply purpose or design. But forget the philosophical debates for a moment. Let's make this personal and concrete. You exist. That's not a trivial fact. It's an extraordinary fact that places powerful constraints on what the fundamental constants, including the speed of light, could possibly be. If the speed of light were much faster than it is, electromagnetic interactions would be stronger. Atoms would be more tightly bound. Chemical reactions would happen more quickly. Stars would burn through their fuel faster, living only millions of years instead of billions. There wouldn't be enough time for evolution to produce complex life. If the speed of light were much slower, electromagnetic interactions would be weaker. Atoms would be loosely bound. Chemistry would be sluggish. Stars might not ignite at all, or they'd burn so dimly that their planets would be frozen. Again, no life. The speed of light we actually observe is in a narrow window that allows for stable atoms, complex chemistry, long-lived stars, and the emergence of life. You are living proof that the speed of light is within this window. Now here's what's profound. If the speed of light has varied over cosmic history, it must have varied in a way that preserved this window of habitability, at least in our cosmic domain. The variation can't have been arbitrary. It has to follow rules that maintain the conditions for consciousness. This means your existence is evidence about the dynamics of fundamental constants. You're not just a passive observer of the universe. Your very presence here constrains what the universe can be, what it can have been, what it can become. Think about that for a moment. You personally are a fact that the universe has to explain. Your consciousness, your ability to ask these questions, is data that any complete theory of physics must account for. In the participatory universe model that John Wheeler proposed, observers don't just measure reality. They create it through the act of observation. The universe doesn't fully exist until it's observed. And observers like you, conscious beings capable of making measurements, of collapsing quantum wave functions, are necessary for reality to crystallize from possibility into actuality. If Wheeler is right, then you're not just living in the universe. You're bringing the universe into existence through your observations. The speed of light is constant because you observe it to be constant. If you could somehow observe differently, measure differently, think differently, the speed of light might be different. This sounds mystical, but it's grounded in quantum mechanics. The observer effect is real. Measurement changes reality. And if you take this seriously at cosmic scales, consciousness becomes a fundamental feature of the universe, not an accidental byproduct. Let me make this even more concrete. Right now, in your brain, neurons are firing. Electrical signals are propagating at speeds determined by the electromagnetic properties of ions and cell membranes. Those properties depend on the speed of light. Your thoughts are literally traveling at speeds set by C. If the speed of light were different, your thoughts would propagate at different speeds. The timing of neural signals would be different. The synchronization of brain regions would be altered. You would think differently. You would be different. So when you ask, what would happen if the speed of light changed? You're asking, what would happen to me? And the answer is, you would become someone else. Your memories might be intact, encoded in the physical structure of synapses. But the dynamic pattern of activity that constitutes your consciousness, the you that's experiencing this moment, would be transformed. In a very real sense, you are the speed of light. You're a pattern of electromagnetic interactions propagating at C. Change C, and you change yourself. Now, you might be thinking, if the speed of light has been changing slowly over cosmic time, has humanity been changing? Have we been evolving not just biologically, but in response to varying fundamental constants? It's a legitimate question. If the constants have shifted even slightly over the past few million years, The electromagnetic properties of atoms would have shifted too. The chemistry of life would have subtly changed. DNA mutations would have occurred at different rates. Evolution would have taken a slightly different path. We have no evidence that this has happened. All measurements suggest the constants have been stable to very high precision over timescales relevant to human evolution. But the question illustrates how intimately connected we are to the fundamental fabric of reality. You're not separate from the universe looking in. You're the universe looking at itself. You're made of quantum fields, governed by constants that might not be constant, existing in a space-time whose structure might be flexible. Every atom in your body, every thought in your mind, is an expression of the deepest laws of physics. And if those laws are not fixed, if they're evolving, if they're in some sense alive, then you're part of that life. You're a moment in the cosmic story of matter and energy, organizing itself into ever more complex forms, eventually becoming conscious, eventually asking questions about its own nature. This is not poetry. This is physics. This is the logical conclusion of taking seriously the idea that fundamental constants might not be constant. So I want to ask you directly, how does it feel to know that you're not separate from all of this? That the question of whether the speed of light is constant is also a question about what you are, who you are, why you exist. Does it make you feel small? Or does it make you feel connected to something vast and meaningful? Now let's talk about the future. Because if the speed of light can change, if it has changed, it might change again. And that has implications for the far future of the universe. Implications for what might be possible. Implications for whether consciousness and complexity can survive forever. The current standard model of cosmology predicts a cold, dark future. The universe is expanding, and the expansion is accelerating because of dark energy. Galaxies are moving apart. Eventually, in trillions of years, galaxies outside our local group will recede beyond the cosmic horizon, their light redshifted to infinity, effectively disappearing from our universe. Stars will burn out. Black holes will evaporate through Hawking radiation. Eventually, in a time span so vast, it's almost meaningless, 100 years or more, even the black holes will be gone. The universe will approach a state of maximum entropy, a heat death where no gradients exist, no energy can flow, no information can be processed, no thought is possible. No life, no consciousness, just a cold, dark, empty void for eternity. This is depressing, but it's based on the assumption that the laws of physics don't change, that the constants remain constant, that the universe we observe now is the universe that will exist forever. But what if that assumption is wrong? What if the speed of light changes as the universe ages? What if dark energy isn't constant, but evolving? What if the fundamental constants adjust themselves in response to the state of the universe? Some physicists have explored these possibilities. Paul Steinhardt at Princeton has developed models of cyclic cosmology, where the universe goes through repeated cycles of expansion and contraction, with the constants potentially changing between cycles. Each cycle might have slightly different physics, might explore a different region of the space of possible universes. Lee Smolin's cosmological natural selection implies that universes evolve, that they adapt, that they improve at producing complexity over successive generations. If our universe is part of such an evolutionary process, it might have mechanisms for avoiding heat death, for regenerating complexity, for keeping the cosmic story going. One possibility is that consciousness itself plays a role in the future evolution of the universe. If observers really do bring reality into existence through measurement, then as long as conscious observers exist, the universe isn't fully determined. It remains in a state of quantum superposition, with multiple possible futures. And consciousness selects which future becomes real. In this scenario, the speed of light in the far future depends on what conscious beings choose to observe, choose to measure, choose to bring into existence. We're not passive victims of cosmic evolution. We're participants, co-creators, The physicist Frank Tipler has explored these ideas in his omega point theory. He suggests that intelligence could survive indefinitely in a contracting universe by exploiting the time dilation near a final singularity. As space contracts, time dilates, and an infinite amount of subjective time becomes available in the final moments before the crunch. If intelligence could manipulate the fundamental constants during this process, adjusting them to maintain habitable conditions despite the changing density and temperature, then consciousness could experience an infinite subjective lifetime in finite physical time. The speed of light would be one of the parameters that needs adjustment. Tipler's specific scenario requires a closed universe that eventually recontracts, which doesn't match our current observations of accelerating expansion. But the underlying idea is profound. If constants can be manipulated, if physics is not fixed, then escaping heat death might be possible. Another possibility comes from the holographic principle and the ADC-CFT correspondence I mentioned earlier. If the universe is fundamentally holographic projection, and if we could understand and manipulate the holographic encoding, we might be able to rewrite the rules. Change the boundary conditions, and you change the bulk physics, including potentially the speed of light. Imagine a civilization billions of years in the future, as stars burn out and the universe grows cold. They've mastered quantum gravity. They understand the holographic structure of reality. They can manipulate the fundamental information from which space-time emerges. They realize that the cold death of the universe is not inevitable. It's a consequence of the current configuration of the holographic encoding. So they reprogram reality. They change the boundary conditions to create new physics, new constants, perhaps a faster speed of light that allows for new forms of energy extraction, new forms of computation, new forms of consciousness. From our perspective, trapped in the current epoch with current physics, this would look like magic. But it would be applied physics, just physics we don't understand yet. And here's the most optimistic possibility. Maybe the universe already has mechanisms for avoiding heat death built into its structure. Maybe the apparent acceleration of cosmic expansion is not driving us toward eternal cold, but toward a phase transition where new physics emerges. Some models suggest that dark energy might not be constant, but could decay, eventually transforming into new forms of matter or radiation. If that happens in the far future, it could reignite cosmic evolution, create new generations of stars and galaxies, give life new opportunities to emerge and flourish. And if the speed of light is connected to dark energy, as some theories suggest, then this phase transition would involve changes in C. The universe would literally transform, its fundamental laws rewritten, opening new possibilities that don't exist in our current epoch. You might not live to see any of this. These are timescales of trillions or googolls of years. But the implications are here and now. The universe is not a machine winding down. It's a living, evolving system with a future that's not yet written. And consciousness, intelligence, observers like you might have a role in shaping that future. That should change how you think about your life, your choices, your significance. You're not just a temporary pattern in a dying universe. You're part of a cosmic story that's still unfolding, still surprising us, still revealing new possibilities. Before we get to the conclusion, I want to address something you might be thinking. How can any of this be tested? How do we move from speculation to science? This is the right question to ask. Science isn't just about creative ideas. It's about testable predictions, reproducible experiments, evidence that can convince skeptics. So let me tell you about the real experiments that are happening now or planned for the near future. First, the cosmic microwave background. We've already learned an enormous amount from satellites like COBE, WMAP, and Planck. But the next generation of CMB experiments will be even more sensitive. The Simons Observatory in Chile, CMBS-4, which is a network of telescopes being deployed at the South Pole and in Chile, and future space missions are being designed to measure the polarization of the CMB to unprecedented precision. If the speed of light varied in the early universe, it would leave specific patterns in the CMB polarization. Different models of varying speed of light make different predictions. We can test these predictions. Within the next decade, we should have data that can confirm or rule out many VSL theories. Second, gravitational wave astronomy. The field is still in its infancy. LIGO and Virgo have detected a few dozen black hole mergers and neutron star mergers. But the next generation of detectors will see thousands or millions of events. Each event is a test of whether gravitational waves and light travel at the same speed across cosmic distances. Each event probes different regions of space with different matter densities and gravitational fields. If the speed of light varies with environment, we'll detect it. Moreover, events at different distances effectively probe different epochs in cosmic history because we're seeing them as they were in the past. If the speed of light has changed over cosmic time, comparing nearby events with distant events will reveal it. Third, very high energy cosmic rays and gamma rays. When ultra-high energy photons travel across the universe, they should interact with the diffuse radiation permeating space, creating electron-positron pairs. This limits how far such photons can travel before being absorbed. But we've detected gamma rays from distant blazars, active galactic nuclei billions of light years away, that are more energetic than they should be if the standard physics is correct. Either there's something weird about how these sources produce gamma rays, or there's something weird about how gamma rays propagate. Some physicists have suggested that Lorentz invariance, the symmetry that underlies the constancy of the speed of light, might be violated at very high energies. Photons with energies approaching the Planck scale might travel at slightly different speeds than low-energy photons. Observatories like the Cherenkov Telescope Array, being built in Chile and the Canary Islands, will observe thousands of high-energy gamma-ray sources. If there's energy-dependent variation in the speed of light, they'll find it. Fourth, laboratory experiments. I mentioned earlier the proposal to use X-ray lasers to look for variations in C. Similar experiments are being proposed using atom interferometers, using quantum entanglement, using ultra-precise atomic clocks. One fascinating proposal involves using atomic clocks in extreme environments, in orbit around rapidly spinning black holes, in regions of intense gravitational fields, in spacecraft accelerated to near-light speeds. If the speed of light depends on the gravitational potential or on acceleration, putting clocks in these environments would reveal it. The European Space Agency's ACES mission plans to put atomic clocks on the International Space Station and compare them with ground-based clocks to unprecedented precision. NASA has similar plans for future missions. These experiments will test general relativity and search for anomalies that might indicate varying constants. Fifth, laboratory astrophysics. Scientists are recreating conditions similar to the early universe in particle accelerators and with high-intensity lasers. The relativistic heavy ion collider at Brookhaven and the Large Hadron Collider at CERN create quark-gluon plasma, a state of matter that existed microseconds after the Big Bang. By studying how electromagnetic interactions work in this extreme state, we can test whether the effective speed of light was different in the early universe. If we see anomalies, if photons behave unexpectedly in quark-gluon plasma, it could indicate that C varies with temperature and density. Sixth, astronomical spectroscopy. When we observe light from distant quasars, we see absorption lines from gas clouds the light passed through. The wavelengths of these absorption lines depend on the fundamental constants, including the fine structure constant, which depends on the speed of light. By measuring thousands of quasar spectra at different distances, effectively different epochs in cosmic history, we can search for systematic shifts in the fine structure constant. Several teams have claimed to detect such shifts, though the results are controversial and disputed. The next generation of telescopes like the extremely large telescope in Chile and the 30-meter telescope in Hawaii, if it gets built despite local opposition, will dramatically improve the precision of these measurements. Within a decade, we should know definitively whether the fine structure constant has varied over cosmic time. Finally, quantum gravity experiments. Multiple approaches to quantum gravity, including string theory, loop quantum gravity, and causal dynamical triangulations, predict that spacetime has a discrete structure at the Planck scale. This would cause dispersion in light propagation, with different wavelengths traveling at slightly different speeds. The effect is incredibly tiny, but by observing photons from gamma-ray bursts billions of light-years away, we can test for it. The Fermi Gamma-Ray Space Telescope has been doing this for years. So far, no definitive signal, but the search continues. Ground-based experiments using ultra-cold atoms and Bose-Einstein condensates are also probing for quantum gravity effects. These experiments create analog spacetimes in the lab where sound waves play the role of light. By studying how these sound waves propagate in different configurations, we can test predictions from quantum gravity theories. So you see, this isn't just philosophy. This isn't just wild speculation. There are real experiments, real observations, real data. The question of whether the speed of light is constant is being tested right now in multiple ways. And here's what's exciting. We're at a unique moment in history. We have the technology to finally answer this question. Previous generations could only speculate. Future generations will know the answer. But you, right now, are living through the moment of discovery. Within your lifetime, we will likely know whether the speed of light has varied over cosmic history. We'll know whether it varies with energy or with gravitational field. We'll know whether Lorentz invariance is exact or approximate. We'll know whether one of the foundational assumptions of modern physics is correct or needs revision. And if it needs revision, if the speed of light isn't truly constant, then physics as we know it will transform. Einstein's relativity will be seen as an approximation, valid in our current epoch, but not universal. The constants won't be constant. The laws won't be eternal. And that will open up possibilities we can't even imagine yet. Now, let me bring this to a conclusion by connecting everything we've discussed to the biggest question of all. What does it mean to be human in a universe where nothing is certain, where even the speed of light might not be constant? Throughout history, humans have sought certainty. We've looked for fixed points, eternal truths, unchanging laws. We've wanted to believe that reality has a stable foundation, that there are facts we can rely on absolutely. But every time we look deeper, we find that what seems certain is actually contingent. Space and time aren't absolute, they're relative. Particles don't have definite properties until measured. The universe isn't static, it's expanding. And now, even the speed of light, the most fundamental constant in physics, might not be constant. This can feel destabilizing. If nothing is certain, if everything can change, how do we find meaning? How do we build our lives? But I want to suggest a different perspective. The lack of certainty isn't a bug, it's a feature. It's what makes creativity possible. It's what makes discovery possible. It's what makes consciousness meaningful. If the universe were completely determined, if every event flowed inexorably from initial conditions and fixed laws, then you would be just a mechanism, playing out a script written at the Big Bang. There would be no real choice, no genuine novelty, no true creativity. But if the laws themselves can change, if the constants can evolve, if observers like you can influence reality through measurement and observation, then you're not just a passive mechanism. You're a participant in an open-ended cosmic story. Every choice you make, every observation you make, every thought you think is contributing to the universe's ongoing exploration of what's possible. You're not separate from cosmic evolution. You're part of it. You're one of the ways the universe experiments with new forms of being. The speed of light, this number we've been talking about for hours now, isn't just an abstract physical parameter. It's the rate at which information propagates, the rate at which cause flows into effect, the rate at which novelty emerges. If that rate can change, if it's been shaped by cosmic evolution, if it continues to evolve, then you're living in a universe that's creative, dynamic, alive in a deep sense. And your consciousness, your ability to wonder about these questions, your capacity to feel awe at the vastness and strangeness of reality is not incidental. It's part of how the universe works. It's part of how the future gets created. Let me get practical for a moment. What does this mean for how you live your life? First, embrace uncertainty. Don't let the lack of absolute certainty paralyze you. Instead, see it as liberating. You're free to explore, to experiment, to try new things, because reality itself is exploratory and experimental. Second, stay curious. The universe is stranger than we imagined, and stranger than we can imagine. Every answer leads to deeper questions. The fact that we're still discovering fundamental things about reality after centuries of science should fill you with wonder. Third, think cosmically. You're not just a person living in a society on a planet. You're a pattern of complexity that emerged from the Big Bang, made of atoms forged in stars, organized by laws that might be evolving. Your choices ripple outward, affecting the future in ways you can't predict or control. Fourth, contribute to the quest for understanding. You don't have to be a physicist to participate in humanity's exploration of reality. Support science education. Stay informed about new discoveries. Think critically about claims. Demand evidence. Ask questions. And finally, recognize your significance. Not in a self-centered way, but in a cosmic way. The universe has spent 13.8 billion years creating the conditions for you to exist, for you to be conscious, for you to ask these questions. That's extraordinary. That's precious. The speed of light might not be constant. Time might not be fundamental. Space might be emergent. Consciousness might be necessary for reality to exist. These are not reasons for nihilism. They're reasons for awe. You are the universe experiencing itself. You are matter and energy organized in such a complex way that it has become self-aware. You are the cosmic story becoming conscious of itself. And the question we've been exploring, whether the speed of light is constant, is really a question about what kind of story this is. Is it a mechanical story, playing out according to fixed rules? Or is it an evolutionary story, where the rules themselves evolve and adapt? The evidence increasingly suggests it's the latter. The universe is not a machine. It's more like an organism. It learns. It explores. It creates. And you're one of its sense organs, one of its experiments in consciousness, one of the ways it discovers what's possible. So when you leave this video, when you go back to your daily life, carry this with you. You're part of something vast and meaningful. The ground beneath your feet, the light reaching your eyes, the thoughts moving through your mind. All of it is connected to the deepest mysteries of existence. The speed of light might not be constant, and that uncertainty, that openness, that possibility is what makes everything interesting. It's what makes science meaningful. It's what makes consciousness valuable. We don't have all the answers. We might never have all the answers. But the journey of discovery, the adventure of gradually understanding more about this strange and beautiful reality we're embedded in, that's what it means to be human. The universe is not finished. It's not solved. It's not complete. It's ongoing, evolving, creating. And you're part of that creation? Thank you for joining me on this journey through one of the deepest questions in physics. I hope I've changed how you see reality, how you see yourself, how you see your place in the cosmos. If you enjoyed this exploration, hit that like button and subscribe for more deep dives into the mysteries of existence. And let me know in the comments, what was the moment in this video that most changed your perspective? What question are you left with? Where do you think physics will be in 10 years? In 100 years? In a billion years? the conversation doesn't end here. It continues with you, with your thoughts, with your questions, with your participation in humanity's ongoing quest to understand reality. The speed of light might not be constant, but one thing is constant: the human drive to understand, to explore, to push the boundaries of knowledge ever outward. Keep questioning, keep wondering, keep exploring, and remember, you're not just in the universe. You're of it. You're an expression of its deepest creativity. Until next time, keep looking up, keep thinking deep, and never stop asking why.